A-level math students, can you solve this extremely tricky geometric series question? So we're told that the second term in a geometric series is e to the 15 minus 6k. The sixth term is e to the 35 minus 14k, where k is a constant. We're given that the geometric series is convergent, and we're asked to first prove that k is greater than 5 over 2. And we're also told that the sum to infinity is greater than 10, and therefore we're asked to find a range of possible values for k. So whenever you're dealing with these geometric series questions, I mean, there's really two things that are sort of crucial to understand about geometric series, is that they're defined by the first term a and the common ratio r, okay? And the idea is, you start at the first term, you just keep multiplying by the common ratio to generate the successive terms of the sequence. And then the other thing is, if you see anything to do with sums to infinity, etc., you're given this formula here, okay, and this formula is valid, right, and this is important to know when the absolute value of r is less than 1, okay? But this formula here, this is sort of the nth term rule for the, geometric series. You're not given this, so you need to remember this, but you are given this formula here. So with that in mind, let's see what we can come up with. So, of interest when you're dealing with these geometric series questions, is, of course, the common ratio and the first term. Now, we're told that the geometric series is convergent, and what that means is that the absolute value of r is indeed less than 1. So we need to use that fact somehow in order to prove that k is greater than 5 over 2. So therefore, we need to see if we can calculate r in some way. So let's firstly write down the general expressions for u2 and u6, right, the second term and the sixth term. So u2, right, well, in terms of the general expression, it's the first term times, r to the n minus 1. So that's r to the 2 minus 1, right, but that's just 1. And u6, that's just going to be a r to the 5. But we know what these are, right? We have explicit expressions for these, two terms, right? This is e to the 15 minus 6k. And this is e to the 35 minus 14k. And you can notice that if I take u6 and divide it by u2, the dependence on the a's is going to cancel, and it's going to leave me with an equation that I can solve for r, okay? So let me just do it up here because I'm going to run out of room at some point. So u6 over u2, what is that? Well, I just use my, laws of indices. This is going to be e to the 35 minus 14k minus 15 minus 6k, right? Just using your laws of indices. And, I'm writing like this just to make sure, you don't miss this double negative. So writing this out, what do we have? We have 35 minus 15, so that's e to the 20, and then minus 14k minus 6k, so plus 6k, so minus 8k. But we know from our general expressions that this is also equal to, well, u to the 6 divided by u2. Again, that a dependence is going to cancel, so just have essentially r to the 5 divided by r, which just gives me r to the power of 4. And then I can just take the fourth root, right, or raise both sides to the power of 1/4. So this tells me that r is equal to, and then again, I'm just going to multiply this exponent here by 1/4 using our laws of indices.